Okay, I think we can start. Hello, everyone, and thank you for joining us. Whether this is your first time joining us or you've been following along since the beginning, welcome. We are excited to have you with us for session 4, where we'll be focusing on practical method development in mixed mode chromatography. Before we dive in, just a couple of quick notes. This session is being recorded, and you'll be able to catch the full recordings along with session 1, 2, and 3 on our YouTube channel. And if you have questions at any point, feel free to drop them in the chat. We'll have time at the end for a live Q&A. Allow me also to introduce our organization. We are a chromatography company based in Chicago, dedicated to designing innovative HPLC columns and compact, user-friendly mini HPLC systems. And with over 20 years of experience, we helped countless labs with customized method development and technical support to solve their most challenging separations. And should you require assistance with any aspect of your chromatography challenges, or if you just wish to explore new column solutions, please do not hesitate to contact us. We are always pleased to collaborate and share our expertise. With that, let's begin today's session, Practical Method Development in Mixed Mode Chromatography. I will now share my screen so we can get started. Hello, everyone. Welcome to today's webinar on practical method development in mixed mode chromatography. My name is Jovana Mitrovic. I'm R&D chemist at Silk Technologies, and I'm thrilled to have you here. Today's session is all about taking what we learned in the previous session and applying it practically, step by step, to develop robust HPLC methods using mixed mode chromatography. So let's get started. Before we dive in, let's quickly recap what we covered in our previous session. We introduced mixed mode chromatography, which is a powerful technique that combines multiple interactions in a single column. We discussed how traditional single mode techniques like reverse phase, ion exchange, or helic sometimes struggle with complex samples. We highlighted how mixed mode columns exploit hydrophobic, ionic, and polar or pi-pi interactions to overcome these limitations. We also showcased our PrimeSep and Nucrom line of columns and discussed some real-world applications. So with that solid foundation, we are ready to move on method development today. So here is what we're going to cover. First, we'll dive into analyte characteristics, how understanding your analyte guides your entire method development process. Then we'll select right column chemistry, choose the appropriate mobile phase, and discuss solution modes. After that, we'll discuss how we fine-tune method parameters and validate the final method. We'll wrap up with an example walkthrough using tryptamine and as well as some phospholipids and thyroid hormones, and that showcase real-world case studies and how we apply these mixed mode columns. So let's walk through the typical workflow of HPLC method development. Step 1, it's usually something like to define the analytes and sample matrix. So we ask ourselves, are we working with small molecules like vitamins or large biomolecules like proteins. And knowing this helps you decide on columns and sample preparation. Next, we have step 2, which is to choose the right column chemistry. Reverse phase is great for non-polar analytes, while ion exchange is better for charged species. Mixed mode chromatography shines when you need to separate analytes with multiple or complex functional groups. Next, we have step 3, which is to select your mobile phase. And usually we work with something like water plus some organic solvents such as acetonitrile or methanol with some pH adjustments and additives like buffers. When we have all of that, we move to step 4, which is optimizing elution mode. We always start with isocratic elution to understand the retention behavior of the analyte. Then we switch to gradient for more complex mixtures. In the step 5, we fine-tune parameters like pH, ionic strength, flow rate, and injection volume to get the best separation and peak shape. And finally, for step 6, we validate and test reproducibility to make sure our method is robust and reliable. So we'll explore each of these steps in detail today, so you'll feel confident applying them in your own lab. So before we can build a successful HPLC method, we need to start with a clear understanding of our analyte. So let's walk through each of the key considerations one by one to set a solid foundation for our method development process. First, let's consider molecular weight. Ask yourself, is the analyte a small molecule like caffeine or a large biomolecule like a protein? Small molecules, which are typically under, let's say, 1,000 Daltons, are usually easier to separate using standard columns. But if the molecule is larger, it might need a wider pore column to allow for a good mass transfer and avoid pore peak shape. Next, let's think about functional groups. Look closely at the analyte's structure. Does it have, for example, carboxylic acids, amines, hydroxyl, or aromatic rings? These functional groups influence how the analyte interacts with the stationary phase. For example, carboxylate groups might favor anion exchange interaction, while aromatic rings can participate in pi-pi interaction with certain columns. Now, we need to consider as well the ionization state and pKa. Is the analyte acidic, basic, or neutral at your working pH? Knowing the pKa helps predict whether it will carry a charge, and that's crucial because charged analytes interact strongly with ion exchange groups on stationary phases. So, for instance, a molecule that's positively charged at acidic pH can be retained using a cation exchange mechanism. After that, let's talk about polarity and log P. Polarity helps us decide what type of chromatography will work the best: reverse phase, ion exchange, or mixed mode. Analytes with high log P values are more non-polar and typically favor reverse phase interactions. On the other hand, polar analytes might benefit from helic or ion exchange interactions. Finally, we need to think about detection. Ask yourself, does the analyte have a UV chromophore? If it doesn't, you may need to consider detectors like LSD, CAD if it's charged analyte, or mass spec to ensure reliable detection. So in summary, by taking the time to carefully evaluate molecular weight, functional groups, ionization, polarity, and detection needs, we can make smart choices about column selection, mobile phase, and other method parameters. So this understanding is the backbone of effective method development. So always begin here before moving to the next steps. So let's continue with analyte characterization by looking at some real-world example analytes such as benzalkonium chloride and understanding how its structure guide our chromatography choices. So let's look at the structure of benzalkonium chloride on this slide. Notice that it has three key features which are highlighted here. A quaternary ammonium group. This is positively charged at all pH values, meaning it will strongly interact with cation exchange groups in mixed mode columns. We also have an aromatic benzene ring. This hydrophobic region is perfect for also reverse phase interaction and can also participate in pi-pi interaction if your column supports them. A long alkyl chain tail, it's a non-polar tail, further that enhances hydrophobic interaction and property of this analyte, and especially when we are working in reverse phase mode. So now let's connect this to method development. Because of the positive charge, we expect strong cation exchange interactions, so we can leverage a mixed mode column that combines ion exchange plus reverse phase. The aromatic ring means we also can have pi-pi interaction if our stationary phase has, for example, embedded aromatic ring as well, so we can have both pi-pi interaction. And again, as already mentioned, the alkyl tail will increase our retention in reverse phase mode. And look at the table on the slide. It summarizes some key features of the analytes and how we can characterize what we are working with. We can see molecular weight, functional groups of these analytes, pKa, they charge at a certain pH, as well as the log P. And by having this kind of structure, it guides our method development process and how we approach column selection. So once we understand our analyte, the next critical step is to examine the sample matrix. The matrix can significantly impact how we set up and run our method. So let's walk through what to consider. First, think about sample type. Is it plasma, urine, food extract, or some dietary supplement? Each of these matrices brings different challenges. For example, plasma often contains proteins that can bind your analyte or interfere with the column performance. That's why we need to consider matrix effect. Complex matrices can cause issues like peak tailing, unexpected retention time shifts, or even solution. And this usually happens because salts, proteins, or other co-extracted compounds can interact with the stationary phase or change the mobile phase ionic strength. So we have to consider sample preparation. And we have to ask ourselves, does our sample need a cleanup step before injection? For example, for protein-rich samples like plasma, you might use protein participation with acetonitrile or methanol. For particulate-laden samples, filtration can prevent column clogging. We also have something like solid phase extraction, which is another great option for reducing interferences. So let's look at a quick example. Imagine analyzing butylated hydroxytoluene in solid deodorant, a waxy, very complex matrix. Here, a simple filtration or solid phase extraction cleanup step helps remove these interferences and protects our column and improves reproducibility. So in summary, understanding your sample matrix And planning appropriate sample preparation helps prevent issues downstream and extend column lifetime as well. So it's an essential step ensuring consistent and reliable results. Now that we know both the analyte and the matrix, next step is to select right column chemistry. So let's also take this step by step. First, think about reverse phase chromatography. RP columns like C18 or C8 are perfect for non-polar or moderately polar analytes. They are workhorses of chromatography, most widely used. Next, we also have something as ion exchange column. If your analyte is charged positively or negatively, ion exchange columns can help you separate them based on their charge. Then we also have something like normal phase or helic columns, and those are usually polar columns and work well for our polar and uncharged analytes. But what if your analyte is complex? That's where mixed mode columns come in. They combine multiple interaction mechanisms like hydrophobic, ionic, and polar interactions in a single phase. And this makes them essentially used for analytes with multiple functional groups or for complex sample mixtures. Finally, let's consider column dimensions. Column length. Short columns from 30 to 50 millimeters give faster runs. Longer columns from 100 to 250 millimeters provide better resolution. Internal diameter of column matters as well. 4.6 millimeter, that's something like a golden standard, but usually 2.1 is popular for LCMS applications. Smaller, also particle size plays important role. Smaller particles give higher efficiency, but require higher pressure. So selecting the right column is all about matching your analyte's properties with the right stationary phase and dimensions to achieve optimal separation. So let's walk through how to select the right mixed mode column based on the key properties of our analyte, using just the simple decision process. So first, we have to ask ourselves, is compound hydrophobic or hydrophilic? Compound is, for example, hydrophobic. We focus on reverse phase-based mixed mode columns. On the other hand, if compound is hydrophilic, we look at the strong polar columns or helic modes. In step 2, we have to ask, does compound carry a charge? If no charge for hydrophobic compounds, standard reverse phase mixed mode columns like PrimeSep or Nucrom, any of them are great choice. If charged, we can then consider the charge type. So for hydrophobic charged analytes, if charge is positive, we can use reverse phase combined with cation exchange columns, such as, for example, PrimeSep 100, which is reverse phase column with embedded acidic group. If charge is negative, we can then use reverse phase combined with anion exchange column like PrimeSep B, which PrimeSep B has reverse phase part plus embedded basic group. And also for cases needing silanol shielding, we can also consider reverse phase plus cation exclusion columns such as PrimeSep B to reduce those unwanted interactions. Now, for hydrophilic compounds, if analyte is uncharged, we can then use a strong polar column such as any of PrimeSep S, S2, and or AP, often in helic mode. But if we have a charged hydrophilic compound, we can use, for example, for positively charged, strong cation exchange column, like prime step S, or for negative charge, we can use strong anion exchange columns such as prime step AP. And by following this pathway, starting with is compound either hydrophobic or hydrophilic, then considering charged and polarity, we can confidently choose the mixed mode column that provides the best retention for our analyte's chemistry. Now that we picked a column, the next step is selecting the mobile phase. And this choice is key to controlling retention, selectivity, and detection compatibility as well. So we typically start with a base solvent system of water and organic solvent like acetonitrile or methanol. Acetonitrile usually gives us lower viscosity, while methanol can provide different selectivity, for example, for certain analytes. Next, we consider pH and ionic strength. The pH affects the ionization state of your analyte and the stationary phase surface, which strongly impacts retention and separation. Ionic strength, controlled by buffer concentration, stabilizes these ionic interactions, sharpens peak, and improves reproducibility. So to help with this, here is just like a table summarizing common mobile phase additives, their types, pKa values, and compatibility with common detectors like mass spec, LSD, or UV detection. And for example, formic acid and acetic acid are weak acids with pKa values around 3.7 to 4.7. They're excellent for mass spec and LSD because they're volatile, and also if using UV detection with them, we have to consider that their cutoffs around 230 nanometers. They also offer lower buffering capacity, which is good for fine-tuning pH, for example, for our buffers such as ammonium formate or ammonium acetate. Now, when we consider ammonium formate and ammonium acetate, they're also volatile buffers, ideal for maintaining a stable pH in the range about 3 to 6, and both are compatible with mass spec and LSD and have similar UV cutoffs such as formic and acetic acid. And also it's worth to mention ammonium acetate works best around pH 4 to 6. On the other hand, we have strong acids. TFA, for example, is a strong acid with a very low pKa, can cause also ion suppression in mass spec, so it should be used cautiously. It's LSD compatible and also has limits UV detection below 220 nanometers. Phosphoric acid and sulfuric acid are strong, non-volatile acids, so they're not compatible with mass spec or LSD detection, but they're transparent and they have very low UV cutoffs. Therefore, they're excellent choice if we are analyzing analytes using very low UV, such as 200 nanometers. So we want to pick additives based on our analyte's chemistry and our detection method. For example, if you plan to use mass spec, volatile acids and buffers like formic acid or ammonium formate are preferred. And when starting method development, start always with a simple mobile phase, like water acetonitrile 70 to 30 with 0.1% formic acid. Then adjust pH or buffer strength, like switch to another additive as needed based on your analyte's behavior. So this table is just quick reference to help you choose the right mobile phase additive for your method, balancing separation efficiency as well as detection compatibility. Once you have your column and mobile phase, it's time to optimize elution mode. So consider isocratic elution first. It's simple, easy to interpret, and highly reproducible. Great for analytes with similar polarity or retention behavior or relatively clean samples. Then we have also to consider gradient elution, which is very useful for complex mixtures with analytes of widely varying polarities. For example, we would gradually increase the organic solvent to help retain and elute all analytes that might have very varying degrees of hydrophobicity. But always start with isocratic to understand basic retention behavior of your analyte. And then, if needed, switch to gradient elution for more effective analysis or shorter runtimes. And choosing the right elution mode balances resolution, speed, as well as reproducibility. When we talk about step 5, this step is where you fine-tune your method to get the best separation and peak shape possible. So let's go over the key parameters to consider. First, pH. Even small changes here can have a very big impact on ionization and retention as well, especially if your analytes are acidic or basic. Then buffer concentration or ionic strength. Adjusting the salt levels helps stabilize ion exchange interactions and can sharpen your peaks. Next up is organic modifier, such as acetonitrile or methanol. They behave differently. So tweaking their ratio lets you control retention time and selectivity. Flow rate is important too. Faster flow shortens your runtime, but may reduce resolution, while slower flow improves separation but takes longer. So also don't forget temperature. Rising the temperature can improve peak shape by reducing viscosity and speeding up diffusion, which then results in giving you sharper peaks. We also have to pay attention to injection volume. Using the smallest volume needed for sensitive analysis prevents peak broadening and fronting. So we have to take into consideration column capacity. So we don't want to overload the column. Diluent composition also matters. So we have to make sure that sample diluent matches as much as possible to the strength of your mobile phase. And this helps avoid peak dissortation or splitting. And if you're running gradient, adjusting the gradient profile, the slope, start and percentage, for example, of the organic solvent, can help resolve peaks that elute close together. So by adjusting these parameters thoughtfully, you can build a method that's both robust and efficient. Therefore, when optimizing your method, always adjust one parameter at a time. This approach helps you clearly see how each change affects separation. We have to monitor some key indicators, such as retention time, how long our analytes stay on the column, resolution, how well peaks are separated, peak shape, we have to watch for tailing, fronting, or symmetry, efficiency, measured by plate count for how sharp or defined peaks are, and as well as back pressure to ensure that system pressure remains within safe limits. And by isolating variables, you build a robust, reproducible method step by step. And it's a systematic approach to fine-tuning, which ensures your method remains stable and reliable over time. Now that your method is developed, The final and one of the most important steps is validation and ensuring reproducibility. First, you want to check robustness. That means making small, deliberate changes in conditions, like a very slight change in pH or buffer concentration, and confirming these don't cause very big shifts in retention time or resolution. We expect some shifts, but that it's not drastic. So if your method is robust, it can handle the little variations that happen in the lab, and we can still have a good separation of our peaks of interest. Next, we have also to test reproducibility by running our method on different days, different instruments, and different column batches as well. So consistent results across these runs give you confidence that your method is reliable, no matter the circumstances. Then conforming repeatability by injecting the same sample multiple times and calculating the relative standard deviation for both retention time and peak area. And when these values are tight and consistent, it's a good sign your method produces dependable data. Also, we have to set clear system suitability criteria. Basically, decide on minimum acceptable values for resolution, peak tailing factor, plate count, so you know when your system is performing well. And to wrap up, this step is critical to ensure your method is ready for real-world use, delivering consistent, trustworthy results every time. Now that we covered the key steps in method development, let's put all of that into practice with some examples, such as tryptamine. This walkthrough will help connect the theory with what we actually do in the lab. So let's start with step one. Define the analyte and sample matrix. Tryptamine is a small molecule with a molecular weight around 160 Daltons. It has a primary amine, which means it's positively charged at acidic pH, perfect for cation exchange retention. It also has an indole ring, which means it can interact through hydrophobic interaction and even pi-pi interaction, depending on the stationary phase. And as we can see here, log P is around 1.55, which means it's moderately hydrophobic. When we have all this data, next step is to select column chemistry. So given the tryptamine's dual nature, both ionic and hydrophobic, we choose Nucrom AH column. And this is a mixed mode column that combines cation exchange and reverse phase, making it just excellent choice for separating and analyzing tryptamine and similar compounds. Now, let's focus on step 3, which is choosing the mobile phase and setting up the starting conditions. Since, as we mentioned, tryptamine has a primary amine group, it's positively charged at acidic pH, making it a strong candidate for cation exchange interaction, plus we know exhibit moderate hydrophobic characteristics. Therefore, when starting a method and first runs, we can start with something simple, like water acetonitrile mixture with ammonium formate buffer at pH 3. This pH ensures that tryptamine stays positively charged, promoting cation exchange interaction with the column surface. Ammonium formate is also a good buffer choice because it's volatile, easy to work with, and compatible with our UV detection, which is 280 nanometers. And if, for example, if we want to after transfer this method to mass spec, we can easily transfer. We don't need to change this additive. So our column and setup here, we are using Nucrom AH column, size 4.6 by 150, which is, let's say, like a standard size of a column for method development. Initial mobile phase condition is 30. We want to start with something simple: 30% acetonitrile, 40 millimoles of ammonium formate, pH 3, with regular flow rate of 1 ml per minute for this size of the column, UV detection at 280, and our standard, which is 1.3 milligram per ml. So this setup gives us a strong starting point to evaluate how tryptamine behaves on this column. And as we discussed previously, we really want to start with isocratic elutions, especially for method development, because runs are simple, helps us understand the behavior and interaction of tryptamine with both cation exchange sites and reverse phase backbone of the column. And also, for the simplicity, we only use one compound in a simple, clear matrix. So what do we see here? Looking at the chromatography here, you can see that tryptamine has a long retention time with our starting 30% acetonitrile. And that's due to combination of cation exchange interaction and hydrophobic retention from the indole ring. So let's now consider what happens if we adjust organic content. From here, we can start tweaking the organic percentage, testing 50% organic and even 70% acetonitrile to see how this affects retention. And increasing organic content reduces reverse phase interactions, as we can see here on chromatograph, helping us find the right balance between retention and runtime. And we can conclude here that 50% acetonitrile is most ideal retention time for this compound and column, not too short and not too long. But after adjusting the organic content, the next logical step is to see how ionic strength, that is buffer concentration, affects tryptamine retention. So let's look at that next. So continuing with step 5, let's talk about the impact of ionic modifiers on tryptamine retention. First, we have ammonium formate test. As we had on previous slide, we tested ammonium formate at pH 3 with 40 millimoles. Higher ionic strength competes with tryptamine for the ion exchange sites, resulting in shorter retention times. And also shown on the chromatogram here. If we reduce ammonium formate to 20 millimoles, lower ionic strength means less competition, so tryptamine binds more strongly to the ion exchange sites, giving us longer retention time. Now, if we change ammonium formate for some other additive, such as, let's say, sulfuric acid, we tried sulfuric acid as an alternative modifier in 3 different concentrations. 0.4%, which is high ionic strength because sulfuric acid is also very strong acid. It weakens interaction between the analyte and stationary phase and results in faster elution. And then by reducing to 0.2% sulfuric acid, which is moderate ionic strength, we increase retention. And then if we reduce even more to 0.1%, which is lower ionic strength, we have strong ionic interaction between the analyte and stationary phase, which results in longest retention time. So what this tells us, compared to single mode columns, mixed mode columns provide greater control over retention time in various ways, allowing for more precise method development. And once we are satisfied with retention time, peak shape, symmetry, and other critical factors, we can then proceed to test our method for robustness and reproducibility. Now that we walked through our method development for tryptamine, let's take a moment just to talk about common challenges, both in general HPLC and especially also in mixed mode chromatography. First, let's look at some general HPLC challenges. Something like pigtailing or fronting can happen when analytes interact unpredictably with the stationary phase. It can distort your peaks and make quantification very tricky. Then there is poor resolution, where peaks overlap, making it hard to separate closely related compounds. Long retention times can also slow things down, especially if analytes stick too strongly to the column. Again, matrix effects are another big one. Complex samples can shift retention or interfere with the peak shape, affecting reproducibility. And speaking of reproducibility, even small changes in mobile phase composition or pH can lead to inconsistent results. And sometimes what's very important is single mode HPLC just doesn't have enough selectivity to handle complicated samples. Now let's talk about mixed mode challenges. With multiple interactions, such as hydrophobic, ionic, sometimes hydrogen bonding, retention can be less predictable at first. It can also lead to peak broadening if one interaction, let's say, dominates too much, or if the balance, if it, let's say, operate in multiple modes at the same time, and if the balance between those modes isn't optimized as well, can lead to poor peak shape. And also precise control of pH, buffer strength, and organic content is crucial. So small tweaks in mixed mode can have a very big impact. So it takes some experience to find the right balance. Too strong or too weak interactions can throw off retention and resolution. But here is the good news. Mixed mode offers just like a real advantages. It gives you greater selectivity, reducing coelution, improving resolution, especially for complex samples, because we kind of have multiple dimensions in a single column. It's also more flexible. You can adjust pH, ionic strength, and organic solvent to dial in retention. And it's often less dependent on extreme pH or harsh solvent, which helps preserve both your column and your analyte. So yes, mixed mode requires careful method development, but it also brings powerful tools to separate analytes that single mode just cannot handle. So now that we covered the challenges, let's explore strategies to tackle them in mixed mode chromatography. Start by fine-tuning the mobile phase pH. It's critical. Small changes can shift the analyte's charge, as well as stationary phase charge, and greatly impact retention. Adjust buffer concentration and ionic strength to sharpen peaks, boost selectivity, especially for ion exchange interactions. Modify the organic solvents type or ratio, switching between acetonitrile and methanol can control hydrophobic interaction, improve peak shape, and depends on the analyte, gives you another selectivity if you switch, for example, from acetonitrile to methanol. Again, choosing stationary phase tailored to your analyte's property is crucial. The right column chemistry simplifies stuff separation, especially for molecules with multiple functional groups. Next, optimize flow rate and column temperature. Faster flow cuts runtime, while a slight temperature increase sharpens peaks. Use gradient elution for complex mixtures. It helps separate analytes with varying polarities effectively. And always balance retention mechanism to avoid over or under retention that causes broad or coeluted peaks. So mixed mode interactions and retention time can seem unpredictable at first, but understanding analytes' behavior and carefully selecting stationary phase makes it like just amazing for achieving complex separations. So controlling mobile phase conditions like pH, buffer, and organic solvent transforms difficult separation in robust, reliable methods. So bottom line is mastering mixed mode interactions just empowers you to confidently separate even the most challenging samples. So let's apply these ideas to a real-world case study, phospholipid separation. The objective was to separate complex samples of phospholipids, like whose structures are shown on this slide. These molecules are crucial in biological systems and industrial processes. The challenge is that phospholipids are amphiphilic with both polar head groups and long non-polar tails. And as you can see from the structures, they differ in several ways, such as the length of their fatty acid chains and the presence of one or two chains. Some even share the same chain length, but differ only in the polar head group. So single mode chromatography often struggles to separate these molecules effectively. For example, in the reverse phase chromatography, if you're talking about single mode, we cannot leverage the ionic nature of the polar head groups, and making it just difficult to resolve molecules that share similar hydrophobic chains. On the other hand, with single mode ion exchange, we lose the ability to separate molecules based on hydrophobicity, so making it hard to resolve those with the same polar head groups. So the solution here was to use LIPAC mixed mode column, which combines hydrophobic interaction for the fatty acid chain with ion exchange and polar interactions for the head group. So this approach allows for effective separation of these challenging phospholipids. So let's take a look at the chromatogram on this slide and talk about results we achieved using LIPAC mixed mode columns. So first, let's set the stage with the experimental conditions. We ran this separation using a gradient of methanol from 90% to 100 with a buffer of ammonium formate and formic acid to support ion exchange interactions. And this setup allowed us to explore both hydrophobic and ionic retention mechanisms. Now let's look at the chromatogram. You'll notice that each phospholipid species is well resolved with distinct symmetrical peaks that are just easy to integrate. That's a direct result of the LIPAC column's dual retention mechanism. So what makes this column work so well? The LIPAC column is designed to handle amphiphilic molecules like phospholipids, which have both hydrophobic fatty acid tail and a polar phosphate or amine containing head group. So here is how it works. The hydrophobic interactions in the stationary phase help retain the fatty acid tails, ensuring that even the most non-polar parts of the molecule stay on the column long enough to separate. Meanwhile, the ion exchange and polar interactions target the polar head groups, differentiating between different classes of phospholipids based on their head group functionality. So this combination of interactions unlock greater selectivity and resolution, just giving us clean, sharp peaks like you see here on the chromatogram, and make it much easier to analyze these complex molecules. Now, let's dive into our second study, where we focus on the separation of iodide, thyroid hormones, and also methimazole, which is antithyroid drug. Why are these analytes challenging? Thyroid hormones have very similar structure, often differing only by number of iodine atoms. They also contain multiple ionizable groups, which means they can interact in complex ways with the stationary phase. And having iodide, a very polar inorganic ion in this example, adds additional complexity. And using traditional HPLC columns can be very hard to separate and retain all these compounds in a single run and column. So how do we tackle this complexity? We use prime-sub-D mixed mode column. This mixed mode column has hydrophobic chain and basic group embedded, making it just ideal for this complex separation. So it combines reverse phase interaction, which helps separate analytes based on their hydrophobicity, with cation exclusion mechanism that adds selectivity for basic compounds. So that's important when we talk about thyroid hormones, because they have primary amine at the low pH will have positive charge, and they're also hydrophobic. So we have for them cation exclusion plus hydrophobic interaction. But if we are talking about iodide, we need to retain it. We have anion exchange for retaining iodide. So on the next slide, we'll take a closer look at the chromatogram and see how prime-sub-D just performs under these challenging conditions. So let's walk through the chromatogram on this slide and review results we achieved using prime-sub-D column, highlighting how TFA and acetonitrile work together to deliver just this excellent separation. We applied a step gradient elution where the percentage of acetonitrile in water is increased after 3 minutes. And this after helps separate analytes based on their hydrophobicity. At the beginning of run, as you can see here based on this table about method conditions, we start with higher concentration of TFA in the mobile phase. This higher ionic strength helps elute iodide quickly. Or better say, at the beginning of run. We wanted to separate it from other compounds. So we wanted to have it at the beginning of run to elute. So that's why we increased TFA. After 3 minutes, we reduced the amount of TFA. This deliberate reduction increases repulsion between the basic groups of the analytes and the stationary phase, which promotes cation exclusion interaction. Because TFA can interact, negative charge of the acid can interact with positive charge of the stationary phase. So it covers, let's say, these basic groups on the stationary phase. When we reduce TFA, we reduce this layer and we increase repulsion. And these interactions, such as cation exclusion, are just extra layer of selectivity, helping separate closely related compounds such as thyroid hormones. And looking at the chromatogram, you can see that each analyte appears as sharp, well-resolved peaks with excellent baseline separation. And what is important, this approach allows for effective retention and separation of iodide ion in the single run with thyroid hormones. Something that, let's say, traditional reverse phase column, single mode reverse phase column cannot achieve, because iodide is highly polar and it's just weakly retained in reverse phase mode. It would typically elute on reverse phase column in the void volume. And that makes quantification very difficult and unreliable. So this method leverages the power of mixed mode chromatography to transform a challenging complex mixture into an effective, robust, and reproducible analysis. It's just a perfect example of how understanding both the chemistry of the analyte and the mobile phase leads to a better separations. So let's wrap up what we covered today and talk about what's coming next. Today, we walk through a step-by-step method development process using mixed mode chromatography. learn how to analyze properties like molecular weight, functional groups, polarity, and ionization, guide our choices in column selection and mobile phase design. We saw also how to optimize elution mode and adjust key parameters like pH, buffer concentration, or organic content to fine-tune our retention. And we explored some real-world examples, such as phospholipids and thyroid hormones, to see how mixed mode chromatography solves these complex separation challenges. In our next session, we'll dive into advanced applications in pharma, biotech, and food analysis. And we'll also discuss new research, innovative stationary phases, and what's on the horizon for mixed mode chromatography as well. So thank you again for joining today's session. If you have questions about the content or need support selecting a column or just want to discuss your specific applications or research, please reach out to us. You can contact us at Silk Technologies through our website, via email, or by phone. And we're just always happy to help you achieve your separation goals. And we hope to see you in the next webinar. And now, if you have any questions, we'll be happy to answer.